Good day everyone. So for today we will review on chemical reaction engineering. Now when we speak of chemical reaction engineering, it covers two topics, reaction kinetics and reactor design. So we will look into each parts as we go along so that at the end, our primary objective is that we will be able to come up with the correct design of the reactor that will facilitate a given reaction. So what is needed for reactor design is the fundamental principles of kinetics. So we will first discuss reaction kinetics. Now, when we speak of kinetics, it just has something to do with how fast a particular chemical reaction occurs. There are four very important factors that affects the rate of reaction. So one is concentration, the other one is temperature, then we have the action of catalyst, and the surface area in the case of solid reactions. Now, in terms of kinetics, we will divide our discussion into constant volume reactions and variable volume reactions. So when we speak of constant volume reactions, these are reactions that are occurring in the liquid phase, or shall I say homogeneous reaction. As such, they are called constant volume reactions. Later on, we will talk about variable volume reactions in which the primary application is in with gas phase reaction. Now, when we speak of rates, actually there are two types of rates. We have the average rate and we have the instantaneous rate. So that of the two, the most or the accurate one is the instantaneous rate because it gives us the rate at the very exact time in which we want to measure it. Whereas the average rate, as the term implies, it gives you the average rate of reaction during a certain time duration. Now, when we speak of the average reaction, it could be expressed in terms of the reactant or it could be expressed in terms of the product. But nonetheless, either of the two expressions for expressing average rate, you have the same formula to use. So let's say for example, you are given a reactant A converted to product B. So when we want to get the average rate of reaction, this time based on product B, all we have to do is get the difference of the concentrations of B, that is the final and the initial concentration, and the time of reaction or the duration in which these particular concentrations we have measured. Now, if we want to express it in terms of A, the difference is the negative sign that we see on the rational expression written on the right side of the equation. You still have delta here representing change, but this time you have used the change in the concentration of reactant A and the time duration or the time elapsed for that particular change in the concentration of A. So in terms of the difference between the two, the first one is positive because it's expressed in terms of the product. The second one is negative because it's expressed in terms of the reactant. So the speed or the rate here is expressed in the average form. So what are the units we have for the change in the concentration with respect to time? So it would be mole per unit volume per unit time. So that would be our rate of A or our rate of B on how it's going to change on a particular reaction that we have hypothetically represented as A being converted to B. Now, I said a while ago that there is a much accurate or a much more accurate way of expressing the rate. So I have already mentioned the units. So it would be mole per unit volume, or that would be molarity, and of course it would be per unit time because we're expressing it in terms of rate. So again, rate could be average or instantaneous, and we're done with the average rate. Now in terms of instantaneous rate, let's consider this particular reaction of butyl chloride with water forming butanol and hydrochloric acid. Okay. In this particular reaction, we have here the first column, the time, and the second column is the concentration of butyl chloride and the corresponding average rate using two values, a pair of values of concentration and time. So in here, we're trying to look, or we're trying to monitor how will the rate behave in terms of the changes in the concentration of the reacting component, which is butyl chloride, because it's our reactant here in our reaction. If you notice, as the concentration of butyl chloride decreases, the rate as well decreases. So this is already like common sense that if there's none to react, then of course the rate would of course decrease. So that is the same thing here. But what is notable is that when you measure average rate, molarity, having unit molarity per unit time, you are taking a pair of values. And the values that you are taking, the pair of values you are taking, are the adjacent pair. Now, what do you think will happen if you take a pair of values that are very far from each other? Like, let's say this is this 0.1 and then this 0.02. Your answer will be very far from the answer that is appearing here. Primarily because you have taken the average of the first concentration and the last concentration, wherein it's very crude because you're starting with the beginning and the end, rather than having it monitored on a certain time duration. And again, notice that it will be very different than the values that you have here. And as such, when we speak of average rate, it is only good for the duration of time in which you are measuring it. That's average. The rate as average on the time duration you are measuring it. In the case of instantaneous rate, though the process is a little bit complicated and like it's tedious compared to the first one wherein we take the average, it will give you a more accurate result. So what you do, you're going to plot. So you will have the x-axis as the time, the y-axis as the concentration of butyl chloride. You will plot the concentration or the behavior of the concentration of butyl chloride as time elapses. So if you see as time elapses, there's a decrease in the concentration of butyl chloride. If you intend to know what is the rate of reaction for a particular time, or that very instant you want to know the rate, all you have to do is project the time that you want to know the rate from the positive x-axis. You go up until you reach the curve that you have drawn. And then you draw a line that is tangent to that point where you have projected the time in which you want to know the instantaneous rate. And then you draw a tangent line to the curve. The instantaneous rate will be the slope of that line that you have drawn. In this case, there are two examples shown here. The instantaneous rate at time 600 seconds is the slope of this line tangent to this curve that you have drawn at 600 seconds. Though again, it's lengthy, the procedure is lengthy and more complicated than the first one, but it will give you the rate at the very instant that you want to know about it, whereas the other one simply gives you the average on the particular span of time that you want to know the rate. So again, we have the average rate and we have the instantaneous rate. Here in kinetics and the things that we use when we design reactors, we are using the instantaneous rate. We're not using the average rate. Now, so in this particular reaction, speaking of now reaction rates in relation to stoichiometry, you have here again butyl chloride forming butanol upon reaction with water. So the rate of this particular reaction could be expressed in terms of butyl chloride or in terms of butanol. And this rate, again, is average rate. Now, if we want to know the relationship of rates with stoichiometry, whether it is the average rate, as indicated here, or instantaneous rate, it would be in principle the same as written here. What do I mean by that? The rates would simply be equal as long as the rates are multiplied to the reciprocal of the coefficients of the particular reaction component in which you base the rate upon. So in this case, you have the rate in terms of A, and as such, you divide it by the coefficient of A in the given reaction. So it would be the small letter A. The rate of B is divided by the coefficient of B in the given reaction. So it's B. The same applies for the product C and for the product D. The only thing that is different here, again, just like in the beginning part of this slide, is that when we use reactants, we have the negative sign before the rates. When we use the products, we have positive, or we need not write the positive sign anymore. So again, the rates are related to the stoichiometry, and we're using the coefficients of the components as they appear in the chemical reaction. Now, next question would be, probably is, will this particular relationship between the rates hold true even if your reaction is non-elementary? Or shall we say elementary? In this case, it's elementary. The answer is yes. Whether your reaction is elementary or non-elementary, this in principle will hold true. The rates are still related to stoichiometry. Now, we have here an example of the ammonium concentration and the nitrite ion concentration in water. So, the reaction is given on top, and you have here the experiment that monitored the corresponding changes in concentration of one as observed against the initial rate of reaction. So, in here, in the first 4 rows, we have kept the nitrite concentration constant, and the last 4 rows we have kept the ammonium ion constant, the concentration constant. And what happens to the observed rate of the reaction? So you have it here. We keep the concentration of nitrite ion constant, and these are the observable initial rates. We keep the ammonium ion concentration constant, and we vary only the nitrite ion concentration, and these are the observable rates. Now, what do you think would be the conclusions that can be derived out of this data taken from a series of experiments for this particular system, ammonium and nitrite ion in water? So you can see that as the ammonium doubles, or the ammonium ion concentration doubles, the nitrite and ion constant, the rate doubles. So let's see. So this is constant. We double the concentration here, and more or less the concentration here also doubles. Now, what about the next? If it's the nitrite and ion that doubles, and we keep the ammonium and ion constant, this time the rate doubles. So notice, the doubling of one concentration doubles also the initial rate of reaction. Let's see if that is true. So we keep this one constant, we double this, like in here and in here, the concentration doubles. So more or less doubles, and this one here more or less doubles. So crudely doubles, that is. So now we say that the rate is directly proportional to the concentration of the two. Why? Because as this one doubles, the rate doubles. When the nitrite ion concentration doubles, the rate doubles. So when we write the rate law, the rate is directly proportional to the two concentration in which we are basing it on, because the doubling of the concentration of one results in the doubling of the rate. And if you look at the stoichiometry of the reaction, 1:1:1:2, if you notice, the rate in terms of ammonium and the rate in terms of nitrite ion would be same, because you have 1 and 1 here. So 1 here and 1 here. We have learned in chemistry that whenever the rate law agrees with the stoichiometry in terms of the exponent that appears on the concentration of the components present in the stoichiometry, then that particular reaction is elementary. Like, since the coefficient of the ammonium cation here is 1, and you see a 1 here as the exponent, the same thing with the nitrite ion concentration having a coefficient of 1 and the exponent 1 is also, and here the exponent is also 1, then we say that this reaction is elementary because the rate law that represents it is related to stoichiometry. So then, reaction is elementary. Whenever the rate law does not have any association with the given stoichiometry, the reaction is said to be non-elementary. The relationship that we're trying to look at would be the coefficients of the components, specifically the reactants, and the exponents of this particular component concentration as they appear in the rate law. If they are the same, reaction is elementary. If not, then reaction is non-elementary. Now, speaking of the rate law, these are your concentration terms, and this is your rate constant. The rate constant is temperature dependent. So we will talk about later how we're going to determine the rate constant. It's temperature dependent, and as such, its value is taken from a series of experiments. Now, as to the exponent in which the concentrations of the reacting components appear in the rate law, if K is empirically determined, the same hold true with the exponents of the concentrations of reactants that appear in your rate law. So, you see the K and the exponents are all empirical in nature. They are not whatsoever related to stoichiometry. So, in terms of the order of the reaction based on the given rate law, so we say that the reaction is nth order in terms of reactant 1 in this case because that is the exponent of reactant 1, and nth order in terms of reactant 2 because it's the exponent of reactant 2. The overall order will be the sum of all the exponents of the concentrations that appear here in your rate law. If a reaction is said to be zero order, you don't see any concentration term that appears. All you get to see is just a K. Now, I have mentioned this already, that the values of the exponents or orders are to be determined experimentally. They are not related to stoichiometry. Now, a zero order is said to be zero because the concentration does not have any effect on the rate, or whatever is the changes in the concentration, it does not have any effect on the rate of the reaction. So it is said to be zero order. A reaction is first order if doubling the concentration causes the rate to double. Why? Because the process here is that whatever you do with the concentration, the same thing is done to the rate. So in that case, they are directly proportional. So we say the reaction is first order. If we change the term doubling here to triple, this will also be triple. So whatever is your multiplier here in the concentration, that would be the same multiplier to the reaction rate. In that case, your reaction is first order. Now, a reaction is nth order if doubling the concentration causes an 2 raised to n increase in concentration. So take note of the pattern here. A reaction is nth order if doubling the concentration causes an 2 raised to n increase in rate. Now, if we change the term here, doubling, we say it will triple, then this will be 3 raised to n. If it will be 4 times, if the rate will be 4 raised to n of the concentration that has been multiplied 4 times, then the reaction is nth order to that particular component in your reaction mixture. So changing this doubling term will change this number here. So take note of the pattern. If you change this to 3, then this would be 3. If you change this to 4, this would be 4. If you change this to 3, the base here will also be 3. So please take note of that. Note that the rate constant does not depend on the concentration. So I have mentioned a while ago that your rate constant K is only dependent on temperature. Now, let's go to specific reactions. So when we speak of first order reactions, I'd like to go straight to the formula that you will use. The formula that you will use would be Ln of the final concentration of A over the initial concentration of A being equal to negative Kt. If you'd like to simplify this, eliminating the Ln, all you have to do is raise the entire equation or make the entire equation the exponent of the E. Then you eliminate the Ln. But nonetheless, whichever formula you'd like to use for a first order constant volume reaction, this would be that formula. So you need the initial and the final concentration together with the rate constant and the time. In terms of plotting, this will require for you to review linearization of this particular equation. So if you will use the properties of Ln, since we have division, this would be Ln of the final concentration of A minus Ln of the initial concentration of A being equal to negative Kt. If you transfer the negative Ln of AO on the right side, your equation will be converted to the form y equal to mx plus b, where your y is the Ln of AT, your m is negative k, your x is t, and your b is Ln of AO. So that explains this particular line here, in which a plot of Ln AT versus t is a straight line with slope negative k and intercept Ln of AO. That same principle we will apply with a second order reaction. So this is our formula for a second order reaction. The y is 1 over AT being equal to Kt plus 1 over AO, AO being the y-intercept. So again, your plot of A over T final versus T is a straight line with a slope K and an intercept of 1 over AO. Now, these two formulas, by the way, came from the differential equation that is appropriate when representing first order reaction. I leave that to you because you have learned that already in your DE. Since this is review, it's important that you have to memorize. If not, make sure that you find the equivalent equation here in your handbook for first order and second order reactions. Now, when you speak of half-life, I suggest that you also memorize these two formulas, the half-life for a first-order reaction and the half-life for a second-order reaction. As the term implies, the half-life is the time it would take for the initial concentration of your reactant to be 50% of its original value, or to drop to 50% of its original value. Please take note that the half-life of a first-order reaction is dependent on the rate constant, whereas the half-life of a second-order reaction depends on the rate constant and the initial concentration of the reacting species. Okay, that's for the half-life. Now, in terms of the relationship of the rate to temperature, I've mentioned a while ago that your rate constant is temperature dependent. And where do we base the dependency of the rate to temperature? So there are two theories which kinetics base the rate of a reaction, and that could be the collision theory and the Arrhenius theory. Now, though we're using most of the time Arrhenius theory, but it would be also beneficial if you know the collision theory, and it's actually very simple to understand. Now, since the rate law has no temperature-dependent term, then the rate constant must be that particular part of your rate law, which is temperature-dependent. So, in here, you have methyl cyanide, and it was observed that from a temperature of 190 degrees Celsius to 250 degrees Celsius, there's a marked increase in the rate constant, and that's from the 2.52 value to 3.16 value times 10 raised to negative time per second. So notice the corresponding unit for K for a first order reaction. So there's an increase in the rate constant. Of course, if there's an increase in the rate constant, we expect there should be a corresponding increase in the rate, because the rate is directly proportional to the rate constant, basing it on the formula. So how do we explain this? So the collision model explains that in order for molecules to react, they must collide. And the greater the number of collisions, the faster is the rate. Now, the more molecules present, the greater the probability of collision and the faster the rate. So, where is the temperature here? We have in the kinetic molecular theory that as we increase the temperature, the degree of excitation of molecules also increases. And as such, there will be a greater tendency for these excited molecules to collide with each other. If there's a greater number of these molecules present, then the probability of a collision, and of course, it translates to a faster rate, is observed. And that is the case of the collision theory. Now, in case of Arrhenius, now we will be basing it on what we call the activation energy. This is just simply the minimum amount of energy required for a particular reaction to occur. Why do we need this minimum amount of energy? We cannot, or a particular reaction is a formation of a new product from a unique set of reacting species. Now, this unique set of reacting species cannot combine with one another unless their initial bonds are broken. So, that energy that is needed to break these bonds is what we call as the activation energy. It's the same thing. It's true with also with anything that if you want to establish a connection with one, you have to break one connection and then you establish a new connection with another. So the energy that is needed to break that connection in relation to kinetics is activation energy. So that's the activation energy. So activation energy is represented as E sub A, and it appears actually in Arrhenius' law. So you have here in this law the rate constant being directly proportional to the product of this pre-exponential factor, which we will be defining later, and this exponential term. So you have the appearance of the activation energy and the temperature in the exponent of this exponential function. Now, if you would be asked, for example, what would be the fraction of your molecules present that will have an energy equal to or greater than epsilon sub A for a particular time, for a particular temperature, what you need simply do is get the value of this exponential expression here. That is the fraction of molecules in which the energy is equal to or greater than the activation energy. That is the fraction of molecules. Now, in the Arrhenius equation, we have the activation energy, we have the appearance of the rate constant, or rather the gas constant. In Joule per Kelvin per mole, the value is 8.314. Your T should be in absolute temperature. So, as I have mentioned a while ago, this A is the frequency factor. And if this exponential term gives you the fraction of the molecule having an energy equal to or greater than the activation energy, the A gives you the probability of a favorable collision. So the equation itself of Arrhenius allows you to measure two things separately. The fraction of molecules having equal or greater activation energy, and this one, the exponential part, and this one is the probability of a favorable collision. Now, both A and E sub A are specific to a given reaction, meaning if we change the system, this activation energy and this pre-exponential factor would be two different terms, or will be a different or having unique different values. Now, if you recall, we can linearize Arrhenius equation by taking the ln of both sides of the equation, and this will be the resulting expression. This will be very beneficial if we're given a pair of t values and we are asked to determine the corresponding rate constant at a different t. Okay, so ln of k equal to negative of the activation energy divided by the gas constant times t plus the ln of A. Now, this is a linearized equation, and as such, it's an equation of a line in which the slope is 1 over t, or specifically the slope is negative 1 over t. The y-intercept is ln of A, and your y is I stand corrected, by the way. The slope is negative EA over R because your variable here is 1 over T. Your y-intercept is ln of A, and your y is the ln of K. Okay, if you have two values, as I have mentioned a while ago, if you have learned already the activation energy, you can determine the corresponding rate constant knowing only one set of K and T given the temperature. Or if you have a pair of values of K's and T's, you can determine the activation energy for a particular reaction. So either which, as long as you fully know this particular formula, you'll be able to know what the particular equation requires in terms of the application of Arrhenius law. Now we go to mechanisms. So the mechanisms are the series of steps that gives us a clear picture on how a particular product is formed from a set of reacting substances. So it also gives you specifically a view of which bonds are broken and which new bonds are formed. Now, in relation to that, we have the concept learned in chemistry, even early chemistry, as to the elementary step. The elementary step in any process is that particular step that only occurs in one direction, or you only get to see one step. You don't have a series of steps, and as such we say that is elementary because you don't have any more a series of reaction, meaning a single step is enough to illustrate how bonds break and how new bonds are formed in the formation of a new product. But if there are a lot of steps to look into, then what you have is a mechanism already. Now when we speak of molecularity is a basic fundamental concept in chemistry as well. It's the number of molecules present in an elementary step. So meaning you don't apply the concept of molecularity if you have a series of steps that illustrate the formation of a particular product from a series of reactant. Molecularity cannot be applied to that. Molecularity can only apply when you have a single elementary step to illustrate a given reaction. So unimolecular if one molecule is written on the left side of your reaction. Bi if you have two, and ter if you have three, even more molecules present on the left side of your reaction. Now, thermolecular reaction is not a common reaction, but according to some writings, it's actually statistically improbable. So if you have an elementary step and you have a unimolecular reaction, then automatically, since your reaction is elementary, it's a first order reaction. If it's bimolecular, then it's a second order reaction. If it's thermolecular, then it's a third order reaction. Now, what about if you have a series of steps to illustrate the formation of the product? Then there is this concept about the rate determining step. In your series of steps, the slowest step is the rate determining step. So it could be likened to any process. The time it would take for the production of anything will be dependent on the slowest part of your process. Its time is dependent on the slowest part of your process. So meaning, if you're going to apply it to the reaction, if you have, let's say, 5 steps, and the slowest of your 5 steps would be the one that will determine the rate of your reaction, because the rest are depending on that slowest step of your mechanism. Now here are examples of elementary steps, because you only have one particular reaction to illustrate the formation of the product from a reactant or from series of reactants or from reactants. And you have here the molecularity, and you have here the rate law as I have discussed a while ago. So bi, ter, unimolecular reactions. These are their elementary steps. Now we go to the concept of catalysis. Catalysis, from the term catalyst, of course, has the presence of a catalyst. The catalyst primarily increases the rate of the reaction. If we want to know the opposite, we have the inhibitor. And in terms of catalyst, we have the what we call the homogeneous catalysis and the heterogeneous catalysis. So if your reaction happens in a single phase, then it is homogeneous catalysis. And your catalyst there is a homogeneous catalyst as well. Now, if it's a heterogeneous catalysis, then your reaction happens in more than one phase. Just like heterogeneous reactions, you have more than just one phase present. This is usually occurring in solid phased reactions, or reactions wherein you have the presence of solids. So in here, we have the first step normally as the adsorption of your reacting species on the surface of your catalyst. So molecules are absorbed on active sites on the catalyst surface. So they get adsorbed first on the catalyst surface because it is there where they rendered ready to react. They are more reactive in the surface of the catalyst. Now here's an example where solid catalysts are used in gaseous reactants and in the cases of catalytic converters in cars. Now, we're almost done with kinetics, and the last part actually has something to do with multiple reactions and reversible reactions. So this one is a parallel reaction, a competing reaction in that sense because you have a single reactant forming two products. When we write the rate law for such, we treat each of these particular branch in your parallel reaction as elementary reactions, and as such, we write it in this manner. So each steps are treated as elementary reactions. So K1CA for the first parallel reaction, K2CA is the second of the two parallel reactions. CA being common, we factor it out, and we can now treat this as a differential equation. I leave to you the treatment of this particular differential equation. This is the rate of the reaction based on component A, your reactant. If you're going to base it on products R and S, this would be your DEs, your differential equation. So for this parallel reaction, you have to take note that at any particular time, the sum of the concentrations of A, R, and S is a constant. So from the DEs that were presented to you in the previous slide, this will be the formulas that you may use. So you have this from the first equation, and you have this from here, a ratio of the rates of the two products will give you this one. So if a particular problem rather is asking for the values of the two rate constants for your parallel reactions, all you have to do is solve these two equations simultaneously. Of course, you have to know the initial values of the concentrations of A, R, and S. So the rest here are explanation as to if the equations are presented in terms of a line. In the case of homogeneous catalyzed reactions, so speaking of homogeneous catalyzed reaction, then it's homogeneous catalysis. The original reaction is written in the form in which you have to write the catalyst concentration both on the left side and in the right side of your equation. And you have to write the rate constant above your arrow presenting the formation part of R and C in your reaction. In this case, we write that the rate of change of the concentration of A is equal to K1CA based in here on your uncatalyzed reaction. Then you form another DE on the second reaction, which is your catalyzed reaction, and you have these two now. Now you notice that you add to the concentration of A here in the original uncatalyzed reaction the concentration of the catalyst. And then you use these two equations for your two differential equations for the uncatalyzed and the catalyzed reaction in here to come up with just one DE. So the reaction for homogeneous catalyzed reaction will proceed even if there's no catalyst present, because the catalyst is simply there to hasten or to increase the rate of the reaction. If you notice, if you take out this term, the value would only be K1Ca. If you add this value, of course, this would be bigger. Then it will give you a faster rate of reaction. If you will process this DE, it will yield an equation like this, wherein the sum of K1 and with the product of K2 and Cc is labeled as the K observed. And this is in the case of homogeneous catalyzed reactions. So making a series of runs at different catalyst concentration will allow you to solve for these two K1 and K2. And this can be accomplished by plotting the K observed against the catalyzed concentration. But if it's not possible for you to plot to get the values of K1 and K2, then treat these two equations directly, this one and this one, without having this particular K observed here, because it will require you to plot. The slope of the plot, if you have done plotting, is K2 and the intercept is K1 in the case here. K2 is K2Cc is the slope, and K1 is the K2Cc is the slope and K1 is the y-intercept if you base it here. Now, if homogeneous catalyzed reactions will happen even without the presence of a catalyst, in the case of autocatalytic reactions, that will not do. So there has to be initially a presence of the product who has a catalytic effect for the reaction to proceed. So we need to write then the product in both sides of your equation, original equation, if the reaction is said to be an autocatalytic reaction. So your product R is acting as well as a catalyst. So in this case, we say as we form more R, the rate of the reaction is expected to increase because it will hasten the reaction. So when we write the rate law, it would be something like this, comparable to that for homogeneous catalysis. Only that this time you have here C sub R, not C sub C. Now you are to take note, just like in parallel reaction, that the total number of moles of A and R at any particular time will remain constant. So if you have initially a total concentration of CO for A and R, at any particular time, the concentration would be equal to that initial concentration. So Ca plus Cr. Now, the formula for autocatalytic reaction may be this without the simplifying expression M, which is equal to the ratio of the initial concentration of the product, which has a catalytic effect, and the initial concentration of A. If you'd like to use this, you will have this particular equation. Please look for the equivalent of such an equation in your handbook. If not, then you have no choice, but you have to memorize, just in case this will be needed by you later on. Now, some product R must be initially present if the reaction is to proceed, mentioned already. The rate will increase as more R is formed. When A is about to be used up, consumed totally, the rate of the reaction will drop to 0. And for this, it's very notable, and please don't forget this, the rate is maximum in the case of autocatalytic reactions when concentration of A and R are equal. The plot of time and concentration for autocatalytic reaction yields a straight line passing through the origin. Now, for irreversible reactions in series, we will just limit it to a two-step reaction in series. You have to stipulate the reaction rate based on the first step and then on the second step. Then you have this You have this for the first step, and you have this, and you have this. That would be your maths. And then in terms of the intermediate, you have the intermediate being a product in the first step and a reactant on the second step. So you see this one. It's the product in the first step, it's the reactant in the second step. This is a linear first order DE, and you will have something like this. You were taught in Math 13 how to process linear first order DE, and this will be your formula in computing or calculating the concentration of R at any particular time, knowing the rate constants K1 and K2. This one allows you to compute for the concentration of A at any time given the amount of K1 and the initial concentration of A. Now, about C sub S, you only have to write down one formula because your S appears on the last part of your two-step series, and it would be this. And noting that there's no change in the total number of moles, just like in homogeneous catalyzed reactions, we have this. And if you have already the CaO known, and you have the values of the Ca and the Cr from the two previous formula, then you can solve C sub S. But if you don't know this, or if you don't want to know this and you just want to go directly to a formula that will solve for C sub S, it would be this formula. So the formula is just dependent on the rate constants again and the initial concentration of A. Notice, class, that you only need the time if you are given the rate constants and the initial concentration, and you will be knowing the value of the concentration of S at any particular time. If K2 is very large, then your reaction is dependent on the slowest step, which is the first step. So your formula in determining C sub S will be simplified in this form. If it's the other way around, if K1 is much larger, then K2 will be the rate determining step. So your C sub S will be computed based on the rate constant of the second step. So the governing step for a series step of reaction is always the slowest of your steps. If we want to know the maximum time, or rather the time in which the value of the intermediate R is maximum, it would be this. It's pre-derived for you to memorize. So all you have to do is know the rate constants. And as to what would be the value of that concentration, it would be this. So you need the constants only. Again, initial concentration and the rate constants. Now, these are very important generalization for a series of two steps reaction. Your A decreases exponentially because it's being consumed in the formation of intermediate R. Your R will rise to a maximum value and then fall, but S is expected to rise continuously because it's the final product. Take note of this. The greatest increase in S is observed when R is maximum. Again, the greatest increase in S is observed when R is maximum. Again, it's, I think, very self-explanatory. Your S will be formed in a faster rate when you have more R available to use. K1 and K2 can be evaluated by noting the maximum concentration of the intermediate R and the time when this particular concentration is reached. Now, in all this generalization class, it's very important that you understand that for this particular reaction, K1 and K2 are not equal, and the coefficients of R and S and A are all 1. If we change any of the coefficients, and if K1 and K2 are not are said to be equal, rather, you have to derive your own working formulas for you to be able to monitor the concentrations of A, R, and S at any particular time. The same true is when you determine the time when your intermediate will be maximum and the corresponding concentration of that particular intermediate. So that would be in the case of irreversible reactions in series, or specifically a two-step irreversible reaction in series. So I will pause here and we'll have another set of recording for the next part of the slide.